Oh, from Bangladesh.
So, shall I start now?
Still, let me share. I think why it's not going to
Okay.
appear.
Are you? Yeah, you just check. Yes, it is coming.
Okay, it's come out. So let me just full
Mm,
view.
Yeah. Okay.
Now
Mm,
it's find it.
Yeah.
Okay.
Gaurav, shall I start? Yes. Okay. So, thank you all of you for joining for today's talk. So, it's my pleasure to introduce today's speaker, Mithun Kumar Das. He is currently Inspire faculty at NISER. So, he did his PhD from HRI. So, from those days, we know each other.
Yeah.
So, and then he was at for some time he was at ISI Kolkata and
Yeah.
then ISER Berhampur and then IMSC and then he was a postdoc at ICTP for some time.
Yeah.
Okay, so now he is at NISER. So over to you, Mithun. Yeah, please.
Yeah. So thank you, Vyogda, for your kind introductions, and thank you all of the participants and all who is here for attending my talk. And the title I put it with general, and my aim is to justify that this topic, that what I'm talking about, this title is justified. All right. Okay, so let me start with some basic, which is basically, I think previously also people talk in the seminar regarding what is concept of equidistribution first. So, so okay. So given a given a in real numbers, you are looking for the fractional part, which is the given algebra, you just subtract the greatest integer part, then which is fractional part. For example, here I write that fractional part of 2.4 is the point. Okay. So here I just took some sequence, for example, square root 2n and fractional part of square root 2n and fractional part of log n. And I run n 1 to 200. Then you see certain pattern. In the first one, you see the point place is quite nice. In the second place, like fractional part of log n, you see that there are so many points in certain place, there is a gap and so on. Similarly, I increase the number of points like 200 to 500. Here you see that the fractional part of square root 2, again, it's nice, that quite nicely distributed. On the other hand, if you look at log n, there is a gap, and some point it is so many points, and somewhere not. So the concept of equidistribution is a kind of the saying, understanding when this regularity, that divided point is appear when your n is sufficiently large. So here I take n is up to 500. But if you take the too large, then how can we see that this regularity appear in the some sequence, and this irregularity is some sequences? Okay, so this distinguish actually defined by the equidistribution theory. So here is the definition. So given a sequence, you look at fractional part, and it's called equidistributed modulo 1 because you are understanding the fractional part. If any fixed interval I subset of the t, if the number of points on average number of points whose fractional part lies in I is converges to the length of the interval. So if you have like since you have finite value points, you can think the left hand side essentially the probability measure, and you just consider the discrete probability measure here and the limit as n tends to infinity what is happening. So if as n tends to infinity, this discrete probability measures converges to the length, which is I call uniform measures, then this the sequence is called the uniformly distributed modulo 1. And on the other hand, you essentially count how many given a fixed interval. So I make it red as a fixed. This is very important here. Any fixed interval, we can count actually. And so any fixed interval, how many points? It's saying roughly n times the length of the interval. you can essentially count this many points in that interval which fractional part lies. So now you have to verify this when this equidistribution happen. So then there's a necessary sufficient condition which is due to while, who says that you don't need to check sequence. Instead of sequence, you just look at the exponential sum. If you look at the exponential sum with for all with k is non-zero, and if n goes to infinity, this limit is goes to 0. This essentially preserves the equidistribution property. So this is the Wald criterion. Actually, it's so this is so far the things like talking about is essentially in the number theory people is considering. We are essentially studying this too much. And here is the example. If we start with the sequence given a real number alpha, which is not rational, then you look at the fractional part of alpha n. Then this criteria, Wald criteria, essentially so that you can essentially directly compute this exponential sum because it looks quite nice. So you can actually use the geometric progression, and you can simplify this way. Then you can find the last term and just simplify this way, that 1 over n times the length of the absolute value of the sine pi k alpha. Since alpha is irrational, so this sign never going to be 0. Therefore, the sequence goes to 0 as n goes to infinity. So therefore, this sequence preserves the uniform distribution property. Now we have several examples. If, for example, alpha n power d, alpha is irrational. D is any degree positive integer, and I also given n power alpha. Alpha is not integer case. Log n power alpha. Alpha is bigger than 1. So this kind of things you can also verify, although it is not easy. So the first case, this alpha n, it is very easy to compute. But this case, you really involving. You have to really understand the theory of exponential sum, really extract the cancellation. Then you can show that this cancellation is very small. I mean, this cancellation give you that n goes to infinity, the exponential sum goes to 0. Okay, so this is kind of we just put as an example. Now we understand given, so everything is as n goes to infinity. Now question is what happened, how we can consider what happened if you consider the sequence with finite number of elements. So like your capital N is finite. So then that means you are measuring the difference here, which is I just call it quantify the uniform distribution. So Dn essentially taking the supreme over all interval I subset of 0, 1, again find a fixed interval. And difference between these two measures, one is the discrete measures and another is uniform measures. Okay. So if this is small, then and as n goes to infinity, this if you try to make it bound, upper bound, and which is goes to 0, then you can confirm that this preserves the uniform distribution property. You can actually prove that. Because this goes to 0, you can just conclude that supreme over all interval this discrete measures converges to the length. So this preserves the uniform distribution property. So therefore, understanding discrepancy is better because you can deal with the finite data. So if you understand discrepancy, then you slowly increase your n, and you say that it's going to 0 or not. Okay. So this is kind of therefore discrepancy is important, and this is kind of we call the effective version of the equidistribution or distribution here. If you measuring Dn, this is kind of effective version. So there is a famous inequality called Eros-Turan inequality, which says that if you start with any real sequence, and then you can say actually discrepancy is bounded by this quantity for any positive integer m greater than 1, you have this bound greater than or equal to 1. M is an integer. So you see that the right hand side, m is a parameter, integer parameter, c is fixed constant, and it's involved the exponential sum. So again, it's kind of related with the exponential sum. So understanding exponential sum is the most important thing here. So if you understand that the exponential sum, that give you a conclusion that it is the if there is a cancellation, you can conclude that this is uniformly distributed. Okay. So alternative way. So if you just note it as a characteristic function, the I for I just define chi as the characteristic function. Then you see that it looks like a limit over n, then sum over the function evaluation at that point of the character, which is converges. So this is here, if you're just a little bit working with the major theoretic argument, like characteristic function bounded approximated by the step function, then every step function can be approximated by bounded continuous function, then you can finally able to arrive in this one, that uniform distribution, that's when limit of the discrete measure converges to uniform measure is equivalent to limit of the function for any bounded any periodic function fn, average of the fn converges to the integration of the f of x dx. Okay, so this is you can actually construct. So this is kind of the idea. So therefore, it actually asks, there are some concept which is the general concept that we first stated here. So this is kind of just starting from discrepancy, starting from equidistribution, and come into this definition. Now we start this with this definition, that sum of average of the function evaluation at xn is converges to the integration of fx in the unit interval. So therefore, here is the some concept, which is if you can starting with some matrix space, xd is a matrix space, then S is finite set, then you can actually introduce, given a finite set on that matrix space, you can introduce the discrete probability measure mu s, which is averaging over the Dirac delta function supported at alpha belongs to S over 1 over S. Right? This is the discrete measures, any finite set you can actually define. And then the question now, if you just increase in the size of S, then you can actually generate the sequence of measure here. So the question is where this sequence is convergent. If this sequence is convergent to certain nice measures, then the concept equidistribution say that weak convergence of this one. That what do you mean by this? So a sequence which is called equidistributed, a sequence of measure or sequence of set here. It's called equidistributed with respect to some nice measure. Mu is here, some nice measure on x. If mu fn weakly converges to mu. What is mean by weakly convergence? It is defined here that every bounded continuous function from the matrix space to C, you have the integration with respect to this discrete measures, which is essentially the this sum of the evaluation of the function at that at on S, which converges to the integration of f with respect to this measure. Okay. So this is kind of any matrix space, you can define this one. And from here, actually, again, you can come to that uniform distribution, or what I discussed already, defined already. And but thing is that you can actually show that this discrete measures here, the counting of the fractional part converges to I, converges to the length of I for any fixed interval. So here fixed, therefore, kind of it's not saying any arbitrary measurable set. Fixed interval is important. So therefore, I think that the weakness is that this is the main means here, that you're not able to prove this result for any measurable set. All you need are fixed intervals here in order to prove this definition, which is number 3 used this definition. Okay. So now we what kind of problem we consider here? So our interest here, the points in the complex plane. So then what kind of points here is the interesting points, for example, the zeros of the polynomials. So you have a polynomial, then we look at the zeros. Secondly, if you have any algebraic numbers, you can also look at their Galois orbit, which is the Galois action of the absolute Galois group to that element, which is fixed, and it is we call it S. If you're not going to the notions of Galois orbit, so given algebraic number, the Galois orbit is nothing but the collection of all roots of the associated minimal polynomial. Okay, so this is called the Galois orbit. And more generally, if you start with the n-dimensional case, your algebraic number is n dimension, then the Galois orbit here is all possible all distinct combinations of the Galois orbits of individual Galois orbits. So you see that there may be, after if you just taking the action of the Galois group to all elements, so there may be so many sequence, so many elements of this sequence may be the same. So you just take the only one element. Therefore, the size of this general case of this Galois orbit is always smaller than or equal to the size of the individual product of the size of the Galois orbits. So you take the individual coordinates, you look at the Galois orbit, then you measure the size. It is not so in the general case, it is not same with the size of the product of all individual coefficients. It is always smaller because there may be some sequence which have the repeating. So we avoid this thing. So this Galois orbit always smaller than or equal to the individual products. Okay. So we are interested in the complex plane, how they are distributed. Okay. So our aim is effective one. That means we already discussed the discrepancy. So here we consider the discrepancy of particular case. For example, if you have a complex number, it's have angles. So how angles are distributed, for that we consider discrepancy. And so when you consider this discrepancy, this is also important to understand in general how this difference in the complex plane. That means you are looking at the discrete measures. You have a complex plane. You have this S we define here, which are all finite, and you are associated discrete probability measures. Then you are looking at what is the given bounded given. So weak convergence is essentially bounded continuous function. But here we considering, since we are aiming the explicit upper bound, so here your F should not be whole bounded continuous function. It should be certain suitable subclass. So the way you choose the subclass, so that on using approximation, you can actually preserve this equidistribution property. That's been using approximation, you can go to the bounded continuous function. That is important. So you want to aiming to get this explicit upper bound. Why we are aiming to this? Because you have a finite data, you have finite element. So understanding this difference is very important, and that from there you can actually check how faster the sequence goes to equally distributed. That you can actually measure from this upper bound, explicit upper bound. Okay, so this is our aim now. And first, you want to see how the zeros given a polynomial, how the zeros of the polynomial are distributed in the complex plane. So here I just put certain very popular polynomial known as Taket polynomial, which coefficient are taking only plus minus 1, and here small p present as a prime. Okay, so I just plot them in Mathematica. For example, that P29 due to 10th prime, which degree of this polynomial is 28. I just plot this. Now I increase the degree of this polynomial. You see the certain interesting here. I just increasing, this is a 20th polynomial, 20th prime, 71. And I think this is 30th prime, and so on. I increasing the degree of the polynomial. So you see there's a very nice pattern. You can find it. So finally, it is the 100th polynomial, 100th prime, 541. This is the polynomial of degree 540. You see the zeros are very nicely distributed. Two ways. One is zeros are very nicely distributed. I mean, angles of these points are nicely distributed on the unit circle. Second is zeros are very close to the unit circle. Right. So this is very ideal scenario one can expect when I mean you are expecting. But question is, if you start with a certain general polynomial, does this model picture is true or not? That is our aim. So we actually look at some general polynomial. So okay, so here I say the two things. One is the angles are nicely distributed on the unit circle. Second, they are very close to the unit circle. Okay, therefore you can actually measuring the two things. One equidistribution along the angles. Another is equidistribution in the complex in the sense that they are closer to the unit circle. Two ways. So first way is, and this, if as I said previously, that I just understand that this difference of these integrations for the algebraic numbers, this roughly preserve the both properties here. If you saw that the function equidistributed for the in general definition I consider, they preserve both. Their angles are nicely distributed in the unit circle. Also, they are very close to the unit circle. These two properties preserved if the sequence is uniformly distributed. So what we will see this thing. Okay. So first we look at the angles. This is called angular discrepancy. So given polynomial. So here you can actually do the very general. You have a polynomial even CZ. That means if you took the coefficient not only rational, that's when your sequence of zeros may not be algebraic. more general, that coefficient may be real, may be complex, still the theory is work. Theory will work. Okay, so then the discrepancy here, the angle. So I just consider theta j's are the arguments, then which is normalized by 2 pi, so that they lie between 0 to 1. Then you define the discrepancy between the points, how many this normalized theta j's lies in I differ with the length of the interval, which is the discrepancy as we defined already. Then there's a famous result by Edwards and Turan in 1950, who established that this discrepancy bounded by 16 times log of L infinitum of the polynomial over n. So what is the L infinitum? So we are taking the polynomial with supremum over the unit circle. Okay. So this is normalized by the a naught, the constant term, square root of a naught. Okay. So many people several people try to improve this bound. One place is 16, another place is this higher mean values, this log of infinite numbers. And people try to get, and the latest result with a group project, this is 21, we established that DS essentially bounded by this 4 over square root pi times HP over n, where HP is some smaller quantity, which is smaller than the logarithm of infinitum. And instead of 16, you can find the 4 over square root pi. So, so this is I can say at this point, this is still not a best possible. And it was you can conjecturally you can find that this instead of 4 over square root, which is like 2.25, which can be make up to 1.75. So there is a space to still work to improve this. Consider this height. HP is considering this height here. Okay. So from here you see that if your polynomial, the coefficient is only constant, as n tends to infinity, your HP or a log of L infinitum always bounded by some constant time log n. That's mean when your coefficient are constant for the polynomial, it's always preserve the uniform distribution property for the angles. Okay. So, but if your HP is large for few cases, that's mean, for example, your coefficient are growth with the exponential of the degree. In this case, it's you can't control the discrepancy size. It's maybe overflow. Okay. So, but constant for the make sure, but you can sure that for constant coefficient, you can always find that this preserves the uniform distribution. The angles are equidistributed on the unit circle. Okay. So this is the result, but interesting fact is that its connection with the analysis problem, which is I little bit discuss here. So essentially we established DS is bounded by 4 over square root C over root pi times HP over N. So C is some constant which is called Fourier optimization constant. What is this? You have some singular operator called Hilbert transform, L infinity norm of the Hilbert transformation at F over L1 norm of the function, and F taking from this certain class of function. What is the admissible? What is the Hilbert transformation here? Hilbert transformation is essentially the principal value of this Fx minus t over t. So it is kind of the singular integral operator. It is actually bounded operator when your function p function belongs to LP, p bigger than 1. At 1, it is not bounded, but p bigger than 1, it is always bounded operator. And in the case of p equal to 2, it is actually isometric. And also, it's have a nice connection with the Fourier transformation. For example, Fourier transformation HF is directly connected to connected with the Fourier transformation of F actually. And this is actually important information we used to solve this problem. And the admissible class we consider here, even continuous non-negative function, whose support is minus half to half, and Fourier transformation is integrable. So this is the class we consider. In this class, you have to solve this problem. Okay. So essentially, we solve this problem and find that C actually 1. And interesting case is that the extremizer not belongs to this class. That's mean we solve this problem and we find the extremizer in the some weaker class, not this class. And the extremizer we consider here as it is, we call it is magic function. It is since it is a special function seminar, so I just mentioned this is as a special function that F is the extremizer, which is looks like 2 over pi log square root log 1 plus square root 1 minus 4x over 2 mod x, whose Hilbert transformation actually sigma function, which is when x lies between half minus up to half, and this other quantity for bigger than 1, which is I draw here. So left side, you see that the function here, so continuity is missing here. Okay. So then if you just using the approximation idea, if you approximate this function as a continuous function, then in this case, you can find that the associated solution actually slightly always bigger than 1. Okay, this happening. So therefore, we don't have the solution in that class. If you break the continuity, then we can show that the c equal to 1. But on the other hand, the lower bound of this you can always find the solution in this class we mentioned here is something 1 plus epsilon. Epsilon is at very small, you can make it so that you can finally reach to c equal to 1. Okay. So this is all like talking about the angular part, angular discrepancy theory. If you have any question up to this part, you can ask me.
Yeah, it is fine. Yeah, you can go ahead.
Okay. So I just move. Now we are interested in equidistribution for algebraic number in the complex plane. So first one, we consider the even algebraic number, even zeros of polynomial, whose angles we are considering. Now instead of angle, we are considering the numbers which is in the complex plane. That means we are looking at the same time angles are equidistributed or not, or also they are very close. They are most of the points are close to unit circle or not. These two property. So now one we will look at. For that, we need certain concept called measuring the algebraic number. There is a certain way, which is called the height of the algebraic numbers, which is defined here. For this, we need something called a Moeller measure. So Moeller measure actually given a polynomial, you can have this product form, and the Moeller measure, instead of modular measure, we define the logarithm Moeller measure. Then Moeller measure is essentially the exponential of this logarithm Moeller measure. So logarithm Moeller measure is essentially taking the integration of the logarithm of the polynomial on the unit circle. And this, using this product formula, you can actually reduce to this in this logarithm of mod CD, the initial coefficient, then sum of the absolute values of the roots. And log plus means all roots which is bigger than 1. That means when your logarithm Moeller measure is small, means it's kind of preserving that all zeros are very close to the unit circle, not far. If it is far, then your logarithm Moeller measure very big. Okay. So there is a lot of study in the understanding this Moeller measures. It is there is a famous conjecture. I not mention although here, but there is a very famous conjecture called Lehmer conjecture, which says that this logarithm measure either 0 or far from the 0. Okay, so it is challenging to. So therefore, people try to construct example so that how close you come to towards 0. Okay, so a lot of work in this direction. I'm not going this direction. And the quantity we need, called it Weil height. So given algebraic number, the Weil height essentially the logarithm Weil measure over degree of the algebraic number. So what is the so given algebraic number, you have a minimal polynomial. You look at the Moeller measure of this logarithm Moeller measure of this minimal polynomial over degree. This is your Weil height. This is called Weil height. And obviously, it's going to be, since you are expecting this logarithm Moeller measure is smaller. This is the height function you are expecting very small most of the case. But the exceptional case is become very large. So we are interested when the situation when this height function is getting smaller and smaller as degree goes to infinity. Okay, and then if you start with the algebraic number which is in the higher dimension, in this case you just took the height function here, the sum of the all Weil height of the individual coefficients. Okay, so this is kind of the high dimension. We need this height function. And now we are about the situation where we are want to introduce the equidistribution result for algebraic number in the complex plane. So for that we need certain restriction. Restriction is that if, as I said, if your algebraic number is unit modulus, that is on the unit circle, from the definition it's trivially 0. So we considering the sequence such that if it is contain infinitely many sequence element from the unit circle, then it is not. I mean, the equidistribution problem is problematic. You can not relate with. So better you avoid that point. The most there should not be infinitely many point of the sequence on the unit circle. Okay, so there it is actually some general situation. So given algebraic number in the hard degree like q bar n, you avoid all proper algebraic subgroups. When it is C cross, all proper algebraic subgroups is basically nothing but a collection of all possible algebraic element on the unit circle actually. So there may be infinite many elements. So we avoid such elements. Okay. So this is called, therefore, such a sequence is called stick sequence. You are avoiding such infinitely many elements which is belongs to that proper algebraic subgroup. Then there is a famous result which is due to Bilu in 1997, which says that if you start with a strict sequence and such that height function goes to 0 as k goes to infinity, and if sk is the associated Galois orbit for gk, then mu sk, the associated discrete power measure, weakly converges to the mu s1 power n. S1 power n is here the polycircle. That means when n equal to 1, it is the unit circle. S equal to 2, it is the torus. We call there is a torus we naturally see, and then high dimensional torus. It is not like if you go to the n equal to 2, it's not sphere. It is a torus. Okay. So then the weakness here again, I just restate again that means every bounded continuous function f cn c cross n to c, the integration with respect to these discrete measures converges to the integration of f with respect to this uniform measure or uniform measure on the polycircle here. Okay. So obviously you can relate with when n equal to 1 case. So this is quite a general scenario. And this result is very important in the sense that it's following several extensions of this result in the several important direction. For example, if we start with a n variable system of n variable n Laurent polynomial equation, this property is known. If you start with a small point over abelian variety, there is a famous result by Shapiro, Ulam, Zhang. They also established this. Not only established this. So this is this equidistribution result they use as a tool to prove some very famous conjecture called Bogomolov conjectures. So also there are some other setting called periodic setting and Rayleigh setting. Although I'm not in this direction, or I may not know very much in this direction, but I just mention if people may interest, maybe look this direction also. Okay, so our interest only the algebraic number here, and mainly I look at the analysis, how analysis give you this equidistribution effective version here. Okay, so what our aim here? So we consider certain subclass or subfamily of bounded continuous function. As I said, for effective equidistribution, you can't consider the whole class, whole bounded continuous function. You have to restrict so that you can speed up certain, so that it speeds up you can speed up the approximation that kind of cover all bounded continuous function. We consider such kind of subfamilies here. So we go any finite set, we are understanding what is the upper bound, so that as s goes to infinity, the size of the s goes to infinity, its speed of this difference goes to 0. That is our m. Okay. And the sequence here, as I said, the algebraic numbers. That means the Galois orbits, the sequence from the Galois orbit. Given algebraic number, you look at Galois orbits. Okay. So here we need to introduce the Fourier analysis because we are interested to study via Fourier analysis. So we want to introduce Fourier analysis on the complex multiplicative group C cross. So the natural is if you just we change for natural looking for the Fourier transformation. We want to define Fourier transformation on C cross. We first transfer it by changing logarithmic polar coordinates. Z going to Z means r e to the power I theta, e to the 2 pi I theta. We change to e to the power 2 pi I theta plus s. That means s looks like log r, right? So we change the z to s theta, and so that your puncture disk, if you have a this puncture disc, this actually going to the cylinder, infinite cylinder. And it became a cylinder because we taking the periodicity here. So therefore, we endpoints are identifying. Once you're not identifying, then it's actually at the rectangular sheet. Once you see that it is, so if you think it is a rectangular sheet, so this puncture disc transferred to some rectangular sheet. Your understanding, considering the measure on this is very easy. The symmetric axis is very easy. So therefore, we transfer this from puncture disc to the cylinder. Okay. So you are expecting all points near the unit circle. That means you are expecting the points on the cylinder actually around the unit circle passing through the origin actually, because r equal to 1, your s equal to 0 means r equal to 1. So that r equal to 1 conform to the complex xy plane. So there you look at up and down the points distributed. You are expecting that most of the point on the cylinder basically toward the unit circle, which is on the xy plane, up and down, these points are distributed. You are expecting like that. Okay. So we transfer this so that our Fourier transformation is natural here, and you can see actually. So when you in this case, the test function we consider here, it looks like f theta s. And we need, in order to define Fourier transformation, we need to define the character set, which is called Pectagonian duals here, which is basically take the C cross to S1, which is actually you can find if I just take only T cross R here, because the C cross, I taking the C cross, not C cross power N. So in this case, the Pectagonian duals, the characters looks like this one, where N belongs to Z and T belongs to R. Then obviously you can now expect the Fourier transformation. If your f belongs to L1, your Fourier transformation looks like the function projection on this characters, which is e to pi this time the measures here, ds times d theta. So you see that here you can take the ds times d theta here because of this change. Okay. And when you have f hat belongs to f hat is integral, the Fourier transformation is integrable, then you have the inverse Fourier transformation. We actually use these things in our proof. So there is a result which is called Peche, who established in 25. He start with the Galois orbit and take the condition that function which Fourier transformation and Fourier transformation of the derivatives are integrable. In this case, they establish this upper bound where CF depend on the constant, depend on the function. That's when you see that the Fourier transformation appear here, time mod t and mod n, and the power of height here, the y light appear here. Then some quantity. It is always challenging to removing this quantity. So this is kind of measuring when a height function is suddenly too small. It is you can't control. So this is this quantity kind of controlling your bad behaviors of this height function, I say. And then 1/3 power is appear here. So you are expecting when 1/3 power is more and more larger, your height function is very smaller. I mean, your height function goes to smaller. So you are expecting the higher power so that your bind going to be tighter, and your equidistribution always expecting how fast you can going to equidistribution. For that, if your power is large, your equidistribution will become faster. I mean, faster speed. If you're small power, the speed is smaller, right? And CF here, see that depend on the function, the Fourier transformation time mod n. This is the result. And we have this result. There is other version, namely February-Livre-Ratelier 2026, Petzker 11, and Messer and Baker in 22. They consider the smoothness on the physical side. That's been directly they consider the assumption on the function is ellipses or some smoothness on the function directly. And they also establish similar kind of result. So our result is here. We consider the class here, the L2 function. Instead of L1, we consider L2 function because you can actually construct, we can use the fact that our final average approximation to go to the bounded continuous function. For that, if you have a function which is L1 intersection L2, which actually dense in L2. So therefore, it is enough to use the function which is L2 function, which Fourier transformation is integrable. And function is automatically continuous because the Fourier transformation is integrable. You can actually, from this definition, directly prove that the function is still continuous. Okay. So this is the class we consider. For this class, our first result joint work with Emmanuel Carnero. 25, we finished this project and we established the following upper bound that given algebraic number whose Galois orbit is S and F belongs to this class and any fixed gamma lies between 0 to half, you have the following upper bound. So here you see that the constant here, it depends on the Fourier transformation times at mod t power gamma and mod n power gamma. So fixed gamma, you actually find a gamma power in the height function here, and on also it's depend. Also here it's depending. So this kind of actually refining and making the sharp class of function. So instead of stronger class, we choose here quite weaker class of function compared to the previous result. And also the gamma here you can allow any fixed gamma up to half. Previous case, it was gamma is exactly 1/3 they prove. But here we have a flexibility. So when you gamma is small, you have a small power t here. That's when function become more, your regularity is increasing for the function. So here you see that you can actually one side, this constant is valid when this is convergent series, right? This is then it is given a constant. So you choosing such function when it is a constant, this series. So therefore you see that this kind of fractional power appear here. So if you look at the previous result, here mod t power is there. If you have a little, actually you can connect this with the kind of derivative, therefore derivative power here. But since this is a fractional power here in our result, you can actually connect it with the fractional derivative, which is appear in the analysis side. So the regularity is less, that's mean. So on the other hand, your constant, you're also having quite sharp constant compared to other previous constants. Okay, so the thing is that if you given gamma, if you fix a gamma, you can and h we define this way. This is best possible upper bound up to this log factor. That's when we get we have an example of the sequence of function and a function f. Such that upper bound we get this one, but lower bound is this. So it is really challenging to removing this bound. Okay, so can we remove this bound? This is still, we don't have any answer. Because of the, because we try to analyze this, try to remove, but we're not able to do these things. So I just keep it this way. And you can compare, okay, we already share the compare. So this is the constant we have our result. And this is a constant, it is previously known. Okay, so 1/3 power here, and here mod t and mod n, but we have some small power. So this is the first result. Now this is the, I just mentioned one dimensional case, but high dimensional case also known. But you see that here our assumption only Fourier side. The assumption is that we start with the function, assuming only the Fourier, that the Fourier side, that Fourier this series is should be convergent. No assumption on the physical side. Now we do the both and also consider general. So as I said, in the general case, the difficulty is the size of the Galois orbit always smaller than the size of the Galois orbit of the individual coordinates product. So therefore we handle slightly different way. So therefore the concept of generalized degree come into the picture here. What is this? So given a n, the high dimensional case, you can actually define the monomial map, which is this way. The coordinates goes to the product of the individual power of the integer powers, right? So this is the monomial map. This kind of going to a high dimension to one dimension, this monomial map. Then the generalized degree is defined by minimum of n not equal to 0, one norm of the integer n times degree of this algebraic number. So this algebraic number, after this monomial map is going to be like in a complex plane, right? So therefore, you can handle the degree. And the observation is when n is 1, your degree is essentially degree of the algebraic number. But when you're bigger than or equal to 2, n bigger than or equal to 2, degree d is always smaller than the degree of the size of the Galois orbit. Sorry, the size of the Galois orbit is always smaller than this generalized degree here. Okay. So we use, instead of degree, we use kind of weaker things called generalized degree in the remaining analysis. And also we observe that height function, this is the condition in the Bill's equidistribution result appear. The height function goes to 0 when the k goes to infinity. And this property also same for this generalized degree. We can verify this thing. It is possible to verify that this is also. And then there is a result by Tiandrea, Narvaez, and Somrat, 27, that Lipschitz, they are assuming here now condition on the physical side, the Lipschitz function, which is too much smoothness they consider here. And they have following upper bound, which is half here, appear half here. And so here the kind of Weyl height, generalization of Weyl height, and then some quantity which you can't remove in the upper bound. But when according to the condition, as the size of the Galois orbit goes to 0, goes to infinity, this quantity always goes to 0. Okay. So then the constant here, they appear in the two sides. The first is coming from physical side, the Lipschitz constant, and second side, if you restrict your function on the unit circle, then you are understanding the Fourier analysis for this restricted function. So they consider the Elon norm of this Fourier coefficient of this restricted function on the unit circle. Okay, you have this quantity appear here. Okay. So we kind of remove this instead of Lipschitz, we try to remove this condition with more weaker scenario. Therefore, the concept of modulus of continuity comes here. Concept of modulus continuity is something is like that. You are looking for the constant, which is after if it's not satisfied certain property of the modulus continuity, it's become a constant continuous function. Okay. So we start with the modulus of continuity. So a function f, that is the test function, is called modulus of continuity omega at s equal to 0. If the difference fixed theta, you look at the difference of the logarithmic radial difference, which is basically looks like omega of modulus. That is called. So when your omega s is c times x, this is essentially the Lipschitz constant, Lipschitz function, right? Lipschitz regularity appear here. And when omega is c times x power gamma any parameter, it is actually, I think analysis later it is called gamma holder function. So you just put it gamma holder regularity here. So we have a general result, but we try to simplify and put the result here for this holder scenario. Here. So we noted HDJ is like kind of height function, which is the smaller quantity than appear in the previously in the literature, time this quantity, which is involved this generalized degree. Then omega x is this holder regular functions this way, where L gamma is the holder constant here. That given f, which is satisfy this modulus of continuity, omega modulus of continuity for fixed gamma like 0 to half, you have the similar kind of bound CF times HD power gamma. So and gamma is any fixed number from 0 to half. Here you see that again similar pattern as Dian et al. Their result. We have L gamma, the constant holder constant coming here, and some regularity. So instead of in their result they have the derivatives, Fourier transform derivative, but here we have L1 one norm of the n for gamma times this, which is essentially connected with the fractional derivatives. Okay. And here we can find actually the best possibility. So we find a function, and we find that there are both upper, and we fix a gamma, and we find that both their upper and lower bound have the same power. Previous case, we find that this is the lower bound is divided by log, but here now they have the same. So here we found an example that we have basically the same upper and lower bound. And you can actually see that their constant. I just again rewrite it here because you can compare this what we get here. So you see that this is essentially equidistribution problems, which is effective return, but it is involved basically regularity of the function. Okay. So kind of analysis and equidistribution mixed together. Therefore, I feel that this is kind of the topic I writing the title this way. And now, how much time I have? Oh, it's 52. How much time I can take?
Yeah, you can try to finish within 3-4 minutes, maybe.
Okay, perfect. Yeah, so I just only give you the very brief idea. So, okay, so we want to estimate the upper bound, want to bound this one. Obviously, you see that this representation imply, as we know, the Fourier inversion, it suggests that you have to put f by its Fourier inversion. Once you put, then here you need suitable simplification. You have to add and subtract suitable things. And then it gets reduced to this form, I1 plus I2, where I1 is looks like this form, the series, this, and then kind of exponential sum here. And I2, it looks like F naught, which is the restriction of the function on the unit circle time this exponential sum. At the beginning, I said that exponential sum is very important, to understand this. So here you see exponential sum appear in this way. Okay. So you have to only first thing you have to estimate this two exponential sum, this exponential sum here, and this two exponential sum. And once you estimate this, then after that you have to put suitable way and certain approximation of the whole series you have to do. You have to find a certain point where you cut the first few terms and then take the tail part. Then you have to estimate both parts separately after putting the value, and then you can estimate the result. Okay. So therefore, challenging is understanding this exponential sum. Even I think in the I2, the exponential sum is more challenging. That is we find here. So first thing, in this exponential sum, the thing is that there is a difference of the. You see that if you look at the series exponential sum, it's the first one is subtracted. So this the exponent come into the picture as a main terms here, first term. So therefore, here it be easy to analyze. So this estimate we can do in the polygon. You can actually, you have a algebra in the whole complex plane. You cut some analysis which include the unit circle. So here you see that the sum over 1 to n for one dimension is essentially mod of log z is less than delta. That means it is an analysis containing your which contain the, I think delta should be less than 1, which containing the unit circle. You choose the analysis which contain unit circle, and then you divide two parts, which is inside this analysis and outside the analysis. So this outside of the analysis, this is kind of we can completely, as I said that you can expect when your height function is small, the most of the algebraic numbers is very closer to the unit circle, and only few points are far from the unit circle. So therefore, here using this idea, you can actually estimate this size in terms of height function. And this one, we actually directly estimate by using the say calculus here. And finally, we get this estimate, which involves the height function here. So you see the height function times infinite number. And I2, which is more challenging one. For here, we use certain techniques, which is one is called the Sur observation, which basically connected the understanding the distribution of zeros of any polynomial with the understanding the distribution of zeros of the polynomial with absolute whose modulus is 1. So you have a polynomial whose the zeros have a absolute value maybe different. Now you remove all absolute value replaced by 1. These two polynomial you can compare by Sur observation. And secondly, we use certain Fourier analytic identity, which basically transfer the exponential sum to certain height function that is appear here. And third thing, we use something called a version of Ziegler lemma. Ziegler lemma is actually more abstract, but we consider certain a very particular case. I written this so that we get this exponential sum with this square root times this square root of height function times n1 now. And the Ziegel version of Ziegel we use here, which is very interesting. So given algebraic number, you don't have a control of the coefficient. Okay. So this Ziegel lemma kind of generate a higher degree polynomial. You can find that this Ziegel lemma is a higher degree polynomial with your controlled coefficient. Okay. So therefore you start with an algebraic number and of degree d, and gamma is any parameter here, which is such that it satisfies this quantity here. And you can generate a polynomial q of larger degree such that this d is here degree of this q polynomial is always smaller than this. And q also vanishes in the same algebraic numbers and its conjugates, also some few other points, because it's is larger than m. Sorry, larger than d. It is a d, capital D is larger than small d. And then the coefficient, each coefficient you can control by the height function. So this is kind of we use inside of our analysis to establish this exponential sum. Okay. And yeah, so here are the references. So I mainly talked about first two references and where I use this few references and here. And this I finished, and thank you very much for your attention.
Yeah, thank you so much, Mithun, for beautiful talk. Okay, so if you have any question, please feel free to ask Mithun.
Yeah.
Okay, so I have one question, Mithun.
Yes.
Like you said, like for most of the polynomials, so like I remember I was studying once a Ramanujan polynomial.
Yes.
Okay, so there we have seen the pattern that the zeros of it is proved that zeros lie on the unit circle. Okay.
Okay, zeros lie on the unit circle, yes.
So all the zeros lie on the unit circle. Still,
Okay.
one can study the equidistribution, right? Whether
Yeah,
those as
yeah,
n tends to infinity, still whether they are equally distributed or not. That can
yeah.
be.
So the two things. One is what are you measuring? You measuring the angles are equidistributed or not, right? Points on the unit circle. But the general equidistribution we define here, the two measuring two things. One is they are equidistributed on the unit circle or not, and also they are closer to the unit circle or not.
So yeah, so for Ramanujan polynomial, it has been proved that all of them lie on the unit circle. On the unit circle. Still, I think one can study the whether they are equally distributed or not, right?
Yeah. This is the angle one, right? Equidistribution means angle one. Yeah, that is true for all cases. That is, you can it is does not matter it is lie on the unit circle or it is far from the unit circle.
Yes,
angles are always exist, so you can understand.
Okay.
Yes.
Okay.
Yeah.
Okay. Thank you so much, Mithun, for really nice
Thank
talk.
you.
Okay. Yeah.